lemma. Is that okay? So let's since there are more people here today than there were last time, so let us recall Dedekind's lemma. Okay, as I was mentioning, like this group theoretic angle, this is one of those independent interesting things. Okay, you can look at it without any reference to algebraic groups. Okay, just uses some group theory and field theory that you, okay, and what does it say? The reason why we are interested in this is that it means a lot to us. Okay, remember what we are studying. We are in chapter 3, right? We are in chapter 3. So let's recall what all we have studied. I mean, it is just a few pages in the book, a few paragraphs. Nevertheless, I think it is very terse material. So those few pages are worth studying for you to think about it for 15 days or a month. There is that much material in there. So, so we studied the structure of commutative linear algebraic groups. So if you take a linear algebraic group which is commutative, then we did make some general statement about this. Okay, and what are the general statements? GS, by which we mean the set of semisimple elements of G, and GU are closed subgroups. I want to remind you that GU is closed in general. There is no problem with that. And what is the proof of this? Because you can think of GU as G intersect GLNU. Okay, so of course that's the proof. That is the one-line proof. What we are doing, what we are saying there is, you can choose an embedding of G sitting inside some GLN. Observe that GLNU is closed because it is just the given by t minus 1 to the n equal to 0. If you write that, now T is a matrix, n cross n matrix. So you expand this t minus 1 to the n is equal to 0. T minus 1 is an n cross n matrix, right? x11 minus 1, x12, x13, etc. You take that matrix, raise it to the n times. You just multiply it n times. What do you get? You get a n cross n matrix again, in which the entries are polynomials in the n square entries, original entries of x, right? You set them all equal to 0, right? So a matrix is unipotent if and only if its entries satisfy these equations. Therefore, it is closed. That's the proof that GLNU is closed. But G is closed in GLN. Therefore, and GU equals G intersected GLNU uses the preservation of Jordan decomposition. Therefore, there is a lot included in that statement. So GLNU is closed, and so when you intersect it with G, you get GU. Therefore, GU is closed in G. Okay, but not so GS. Right? GS is you cannot say it is closed in general. In fact, if you take a group like GLN, for example, GL1 is maybe a bad example, GL2, then the set of semisimple elements is not at all, is far from being open. In fact, it is dense, far from being closed. It's a dense open set. Okay. So this is special that GS is closed and GS and GU are subgroups are really need the fact that G is commutative. Okay. And we also had GS cross GU to G by the multiplication map. This is an isomorphism of algebraic groups. And the point here in the proof was that the non-trivial part of the proof was showing that what is clear is that this is a bijection of groups. It's clear that it is a homomorphism of groups. It's clear that it is a morphism of varieties. All that comes sort of for free. So the non-trivial part is to show that the inverse map is a map of varieties. That's the part that is non-trivial. Okay. So we had this structure theorem of commutative linear algebraic groups, and then we have the structure theorem for linear algebraic groups of dimension 1. Connected. Here I am not assuming anything. Here I am assuming it's connected. So if you have a connected linear algebraic group of dimension 1, then some later theorem 3.6.9 or 4.9 4.9. 3.4.9 says then G is equal to Gm or G is equal to Ga. The only connected linear algebraic groups of dimension 1 are, you think of the field K and consider it as an additive group, that is Ga, or you take the invertible elements of the field, in other words everything other than 0, look at it as a multiplicative group. This can be realized as this is the group underlying the variety. When you throw, so as we observed last time, if you have an affine space and you look at the open set where a given function f is non-vanishing, that of course is an open set here, but you can think of that as an affine variety by identifying it in putting one more dimension as in an plus 1 as a subset of closed subset of an plus 1. Right here Gm, what do we mean by Gm? It is in the affine 1 space, you can think of it as the complement of the 0 set of the function x or t, whatever that function is. The only function, the only point at which t is equal to 0 is 0 itself. So the complement is all the non-zero points. That is you can think of that as an affine variety, and if we do, then it does become an algebraic group. The group structure is clear. I am doing this just to tell you what it is as a algebraic variety. So, and it becomes a linear algebraic group. Okay. So it is either that group which we denote Gm or this group. Okay. Now, as I was mentioning, this 3.4.9 we will not do the proof. So this is without proof. However, we did do something So 3.1.2 says the following. .3. So while we cannot do this, that's a little difficult for us to do in the course. It will take up a lot of time and into things that maybe we won't, that I don't think are really essential for an understanding of the rest of what comes after that. So it sort of takes you on the side, takes you slightly tangentially. That's the reason we are not worrying about the proof of this. But among the things that, so if this is the theorem, then at least you have to show that G is commutative, because these two are commutative. So we are showing G is commutative, then meaning connected linear algebraic group of dimension 1, then G is commutative, and all this we have shown, and the proofs are non-trivial, and you should study the proofs carefully and analyze the proofs. Okay, that's very much part of the course. So either G is equal to GS or G is equal to GU. So if it is this, then the first one is true. If it is this, then the second one is true. So we have proved this this thing. And then if G is unipotent, that is in this case, recall that a group is called unipotent if each of its elements is unipotent. If G is unipotent, then, well, it must be this, right? In particular, if you take any element of the underlying field, and if you are in positive characteristic, then you add to itself p times, it becomes 0. So it has order p. So that is the statement that we proved. If G is unipotent, then every element, non-trivial element, of G has order p, okay, if characteristic p is bigger than 0. That's the assumption. Characteristic of k equals p bigger than 0. Okay, which we also proved. Okay, then we were doing the next thing. Right, the next stop is called diagonalizable groups and tori. So definition, a linear algebraic group G is diagonalizable, and as we said last time, when is it diagonalizable? The most natural thing is to assume it can be realized as a subgroup of the diagonal matrices in some GLN. Okay, we know that it can be realized as a closed subgroup of GLN for some n. But now, if it can, actually you can make it sit inside, maybe some larger n perhaps, doesn't matter. If you can make it sit inside the diagonal of GLN, right, then you call it diagonalizable. It makes sense. Okay, is diagonalizable if G is realized as a closed subgroup. Realized meaning is isomorphic to as a linear algebraic group, as a closed subgroup of Dn is equal to invertible diagonal matrices for some n. So that's the definition. Right, and then we had we defined characters, and the reason why we need Dedekind's lemma is that it is crucial to us in the study of diagonalizable groups and of tori. Okay, so this is our definition of a diagonalizable group. Now we give the structure theorem for diagonalizable groups. Okay, so here is the structure theorem for diagonalizable groups. So 3.2.3. So I'll maybe say that. So let me do it here. 3.2.3. So this is a structure theorem for diagonalizable groups. So the statement is the following are equivalent for a linear algebraic group G. First, it's a structure theorem for diagonalizable groups. So the first condition is, of course, G is diagonalizable. Right. 2. Now, if you look at the characters of G, by characters we mean linear algebraic group homomorphisms from G to Gm. Okay. As we observed last time, this gets the structure of a group, abelian group. You can multiply two characters pointwise and you get another character. Okay. Now, this group is written additively. Because it's an abelian group, it's convenient to write it additively. Okay. Now, so the set of characters must form a basis for the ring of functions of G. So let's see. Let me this is our notation for the group of characters is a finitely generated abelian group and spans Kg as a k-vector space. So characters are, in particular, what are characters? They are maps from G to Gm. Gm is just k star. So you can maps from G to, these are morphisms. So morphisms from G to k star, are, you can think of them as in particular morphisms from G to k. So they are functions in particular. So as functions, they span this k vector space. Okay, and the third is, if you wish, as we were saying last time, this is a characterization in terms of looking at it as a subgroup. This is a characterization in terms of the coordinate ring, and the third characterization is a representation theoretic characterization. Okay, so it says that every rational representation is a direct sum of one-dimensional representations. So every rational representation is a direct sum of one-dimensional representations. Okay. Now, where this comes in I mean, this is this sort of is it's difficult to say where exactly it comes in. It is sort of pervades the whole thing. It's very basic underlying fact in all these considerations. Okay, so let us recall the statement. So this is nothing to do with algebraic groups, just you have a group and a field. It has to do with functions from that group to that field. Okay, so G is an abstract group. I repeat, the word abstract may be looking strange because what is a group? All groups are abstract groups. But the reason why we say abstract group is because to distinguish it from linear algebraic groups. You're just thinking of it as a group, as a set with a group structure. Okay. G abstract group, K a field, any field. So maybe I'll call F. Because because our field K is assumed throughout to be algebraically closed. Right now, I'm making no such assumption. Okay, F any field. The characters of G with values in F or values in, this means the non-zero elements of F which form an abelian group under multiplication. Okay. Is just group homomorphisms from G to this, right. So the claim is Hom as groups from G to F star. You can think of this as sitting inside set maps from G to F, just by composing by the inclusion from F star to F. Now this is a vector space, this is an F vector space by pointwise addition and scalar multiplication. Right, and the statement Dedekind's lemma says this is F linearly independent. So as a subset of this vector space, you can talk about a subset of a vector space, finite, infinite, doesn't matter what it is, linearly independent. So what does this mean? You take any finite number of them, and if you take a linear combination of those elements as elements of this vector space with coefficients from F, and you write A1 chi1 plus A2 chi2 plus dot 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 A n chi n equal to 0, then all the AIs must be 0. This is what it means. Okay. Okay. So let's prove this. I hope you tried and succeeded. So last time we had left it out as an exercise for you to try after doing some baby cases. Okay. So let's work it out. Okay. It's not very difficult. So so let's last time we did it by just doing it with for 1, 2, etc. But so this time let us just try to write out a formal proof. Okay. Let's see. Again, this might not, I'm just doing it on the fly. It might not be the most efficient way to write it, but nevertheless, hopefully it will be a proof. Okay. So suppose not. So assume that there is a non-trivial linear dependence relation among the characters. Okay. Then as you always do in mathematics very often. You try to find, you want to prove something is not possible, so you try to you try to find sort of an ideal member which violates your hypothesis, right? A minimal member, right? So what we should do is the natural thing to do is let n be the least value for which there is a non-trivial linear, you can find n characters among which there is a non-trivial dependence relation. Okay, so let n be least such that there exists a non-trivial dependence relation. There exists chi1, chi-n in Hom. These are characters. So group homomorphism from G to F star such that there exists and a non-trivial relation a1 chi1 plus an chi-n equal to 0. The non-trivial means not all ai are 0. Okay. Okay. Now the idea is to
So you are saying that it's the least, so I said none of the.
Yes. So in particular it follows that none of them is 0, because if one of them is 0, then it comes down, then n is violated. Okay, it follows. Okay, right. So, may assume a1 is equal to 1, right? Because a1, I know, as Arghya correctly points out, none of them is 0. So in particular, a1 is non-zero. And so I can multiply by a1 inverse. Okay. Okay, so let's write it out. Chi1 plus a2 chi2 plus an chi-n equal to 0. Okay. Now let me see what I want to do with this. The idea is somehow to write two relations, use the fact that these are characters, use this relation to write one more relation, and then subtract the two relations, so that when you subtract you get a one that of lesser less than n, and hopefully you will also be able to get it non-trivial. So it will become a contradiction. This is the idea. Okay, so let's try to do that. So the fact that these are characters, I have to use g, you know, the chi1 of gh is chi1g times chi1h. Okay, so let's write that. So I can also write, let's see, let me write it like this and see if you agree with okay, what have I done there? What I have done is, I have evaluated the first equation on GH. So, okay, I'm skipping writing it, but I will not write it, I will just explain it. Put a GH, 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 or an HG, HG, HG. This you can write as chi1 of H times chi1 of G, A2 chi2 of H, chi2 of G. But then G is general, so I pulled out, I can erase the G. That's all I have done. This is true for every H. Okay? Okay. Now, okay, so there you go. You have two things. So I can maybe multiply this by chi1h and subtract. Okay, so take star, this is 1, this is 2. Arco doesn't look happy. So let me is that should so what I mean is, see, I am writing this right. I can evaluate this at a point hg, and then use chi1 of hg is chi1h times chi1g. So to write this out, but then this holds for all g. So, and therefore as functions I can erase that. That's what I've done. Okay. Now let's take, so what I'm doing is chi1h. So right now this is true for all h. I'm also keeping h. At the moment I will specialize h, but I'm not doing it at the moment. Okay, times 1 minus 2. So multiply this by chi1h and then subtract this. What do I get? Here I get 0, right? This I have multiplied by chi1h minus a2 right. Okay, so now that's a linear dependence relation among fewer than n elements, right. So it must be that it is trivial. Okay, so by choice of n I get a2 chi1h is equal to a2 chi2h, but this is for all h. Therefore I can erase the h. So a2 chi1 is equal to a2 chi2, but a2 is non-zero. Since let us take this to be distinct here. Okay, so I am assuming this to be distinct, and then I get contradiction. Okay, because I've assumed these to be distinct, now I get chi1 equal to chi2.
N is least, so it will be distinct, right?
Pardon me?
N is least, so it will be distinct.
N is least, so it will be distinct. Correct. Correct. All right. So in the sense that, see, you could have taken chi1 minus chi1 equal to 0. In that sense, when you can't quite say your argument, although I agreed a minute ago, it's not quite correct, because if I write chi1 minus chi1 equal to 0, but then if I collect all the terms, it becomes 0. See, when you might have a non-trivial relation to begin with, which when you collect the terms, if you to reduce it, you make it, you have to collect it, and when you collect it, it might become 0. In any case, it's a minor, it's just a matter of this is called hair splitting. Okay, so this is just however you write it, it doesn't matter. So you either, it's clear that you can choose them to be distinct, and therefore we have a contradiction. Okay, is this all right? Okay. Okay, so let's see, where were we? So let us try to prove 3.2.3 now. This is where we were. Okay. So what should I erase? Maybe I can erase this. Now we are clear about the statement and the proof of Dedekind's lemma. So let's go 1 implies 2. So proof of 3.2.3. Okay, I repeat, the proof again is quite subtle, and I want you to pay, this is one of the important parts of this course, is to analyze all like the previous two proofs. This proof also, you should have it, you should analyze it, internalize the proof. Okay, and what is nice is it will mean in the end something in group theory which is not at all obvious. Okay, at the end of the day, you will have reached some point, and if you specialize to just say finite groups and complex numbers for the field, you get some statement which is usually proved as a theorem in books on group theory. Okay. Okay, so we want to prove 1 implies 2. So G is diagonalizable. So G is subset of some Dn, right? Closed subgroup of some Dn, right? That's what G is diagonalizable means. It is realized as a closed subgroup of Dn for some Dn. Right? The closed is not so, it comes for free. In the sense, if you can embed it into the diagonal subgroup of GLN, then the closed is obvious because any image of a algebraic group homomorphism is closed. Okay. Now, what did we, when you have a closed subvariety of an affine variety, there is a map in the reverse direction, and that's onto, right? So you have a map K Dn. You can restrict functions, and every function is the restriction of some function from above. Okay, so it is important that these be affine varieties. See, it is important. See, for example, if you know a little bit about projective space, you can take an affine space and put it inside a projective space. Affine space has lots of functions. The projective space has only constant functions. So you can't say that there is the map is onto. It is important that the space that the bigger space is an affine space. It has lots of functions. Okay. Okay. So this is onto. Right. Now, what is this? this we know is right, and this has this property chi star dn. So this we observed last time is equal to right. It is the free abelian group on n generators, and you can think of these as so what is a character? The character will just be T1 to the A1, T2 to the A2, Tn to the An, where A1, A2, An are integers. Okay, we proved this last time, didn't we? In any case, so you should. I think we proved it towards the end of last time. Even if you haven't proved, you should try to prove this as an exercise. And if you do not, is there something you do not understand? Please do ask me on Friday. Okay, so this should be very clear to you. Why? So take this. This is an example of a diagonalizable group is Dn itself, because by the very definition, and in that case, why this is true should be very clear. Okay, so here it is a what is called a Laurent polynomial ring. It is generated by monomials in T's. With monomials, of course, in this case could have negative exponents, negative integral exponents as well. Okay, so and therefore it is clear that this here it holds, right? So clear that chi star dn is a basis for a k basis for right. Okay, now you have an onto map. You take a basis here, and so the image of the basis, I am not saying the image of the basis is a basis, but the image of a basis is a spanning set for this, right. Okay, so what you know is that image of chi star dn in Kg is a K spanning set for Kg. Right. All I am saying is you have a basis here, look at its image in an onto map, that is a K spanning set. Okay. Now what do we have to, are we done? So claim is, now I claim the following. So take a character of G, think of it as a function, write it as a linear combination of restrictions of characters from Dn, right, and then use Dedekind and see what you get. Okay, that's the next step. So let's do that. So I'll erase this. Okay, so let chi be in chi star of G. What does this say? So image of chi star Dn is a K spanning set for Kg. So this chi is in particular a function. Okay, so write, and therefore it can be written as write chi is equal to A1 chi 1 restricted to G plus An chi n restricted to G with Ai in K and chi I in X star of Dn, or maybe not n but some other S. Okay, right? It is, what is the image of X star Dn? In what does this mean? This is just the restriction of a function from Dn to G, right? So I take characters here. So all the characters, restrictions of all the characters is a spanning set. So in particular this chi, okay, but chi 1 G is a character, chi S, all these restrictions are characters. So what does this mean? If you were able to write this, you would get a non-trivial. The only way this can be is if chi is the restriction of a character by Dedekind. Therefore, see, this cannot be unless chi is equal to one of them. If chi were distinct from all of this, you would get a contradiction by Dedekind. So by Dedekind, chi equal to chi I sub G for some I. Right? So in particular, you've shown that every character is the restriction of a character from Dn. Okay. Okay, now we are so right. Now we have done. We are done. Is it a finitely generated abelian group? Yes, because it's the homomorphic image of a finitely generated abelian group. And do they span Kg? Yes, indeed, because the restrictions of these formed over K, for KDN, this was a spanning set, and that is on to, and therefore it's the images are a spanning set for the Kg. Okay, so this proves. So let's see. So corollary or proof exercise. Let H be finite abelian groups show that a homomorphism, any homomorphism from H to the complex numbers, non-zero non-constant numbers, can be extended to, is the restriction extends to a homomorphism of G to complex numbers. I claim we have proved this. Question is, you have to see why we have proved this. That's the exercise. Okay, that's a statement which I could have given you at the beginning of the course, right? Okay, these have nothing to do with algebraic groups. Just the finite abelian groups maps into any homomorphism, group homomorphism this is. Okay. Anyway, so that's an exercise, you think about it. Right? It may be obvious, but in any case, you should understand this thoroughly, why this statement has been proved. Okay, and maybe also how much can I, there are many assumptions there. Abelian groups, C star. So can I put some other field? I mean, there are things that there are many things that are, that can be changed there. And how much of it can be changed, how much can you not? Okay, so that is for you to think about. It's a sort of open-ended exercise. Okay, so that does 1 implies 2. Okay, let's see. Let's see, 2 implies 3. Okay, that's the part that is really worked. 2 implies 3 is the part that is the most difficult part, and it's like the proof of, we'll follow the proof of the book. Okay, it's very well arranged. It's a very clever proof. It's not perhaps the proof that you would think of the first time you would try and write the proof. If I were to try and do the proof by myself, this is not something I would come up with immediately. But once you think about it and you arrange it like that, it comes out, of course, very efficiently and beautifully. Okay, so let us just try to follow the proof of the book and understand it. Okay, now let's see, 3 implies 1 is obvious. What does that mean? So you put G inside some GLV. This, of course, you can do without any assumption on G. Right? So this is always true. Now I know that every rational representation is a direct sum of one-dimensional representations. This V I think of as a rational representation of G. It is a direct sum of one-dimensional representations, which means that there are common eigenvectors for all elements of G. That's what it means, right? So, if by 3 V has a basis consisting of common eigenvectors for all elements of G. Why? If you can write this as a direct sum of one-dimensional representations. Each one-dimensional representation take an element of that one-dimensional space. That is a common eigenvector for every element of G, because you multiply by G, it is some scalar times that element, right? Okay. What does that mean? So you write G, I mean you choose that basis for V and write a matrix for GLV with that basis. Where will G go? G is sitting inside the diagonal, and of course I don't have to care about, see, the fact that it is a closed subgroup comes for free. So in this basis, so in such a basis, with respect to such a basis, G is contained in D. Right? Okay. Now let's do the part that is the most difficult. So 2 implies 3. Okay, so right, let G to G. So you are given a rational representation. Our job is to show that it is the direct sum of one-dimensional representations. Right. Okay. So the idea here is so each one-dimensional representation, if it's a direct sum of, see, let's think about what we have to show. So each one-dimensional representation defines a character of G, right? Because so you fix why? How does it do that? You fix one basis vector of that one-dimensional representation. Each element will give you multiplied by some factor. That factor must be a character, because G to GL of that is a homomorphism. Okay, so characters are precisely one-dimensional representations, right? Okay. Now, so the idea is the following. So each one-dimensional representation defines a character. Of course, several of these could give you the same character, right? I mean, there is no reason why it should not give you the same character. Okay. So now you collect, sort of you break them up. This is just like you would want to break up. See, you give me if you give me a linear transformation on a vector space. Let's say we are on an algebraically closed field as we are. Then you can think of eigenspaces, and you break up the. So if you are given a vector, if you are given a diagonalizable semi-simple linear transformation, you can think of eigenspace decomposition, right? That's more natural than breaking it up into one-dimensional spaces, because those one-dimensional spaces are not unique, but the eigenspaces are unique. Okay, so it's natural to try and break up into eigenspace. That's a canonical decomposition. Okay, here again, what we are doing. So here, you instead of just one linear transformation, you have a whole bunch of commuting linear transformations. Okay, so they are well, well, at the moment, okay, at the moment you might say, why do I know they are commuting? Okay, it's not clear that they commute at the moment. Okay, okay. So, but anyway, in the end they will commute, right? That's part of what we have to prove. Okay, so what you do is try to club. So instead of one, you have several, and you so there is an eigen. So the space corresponding to those elements which transform as a given character will be on, you set them up into several pieces, and the way to look at this proof is, what he's trying to get at is, what are, so these projections from V to these spaces, generalized, eigenspace, common eigenspaces, what are the projections? So he will write out something very, sort of very cleanly. As I said, it's not something that you might think of at the first go, but, and then these projections, you will get nice expressions for those projections. Okay, is it clear what we are doing? So what your aim is somehow to use the hypothesis and try and get a expression for what the projections must be. Okay, so well, if what I said is maybe a little vague, never mind, it will be clear in the, it is just a sort of introductory to the proof. So this is made precise in the proof itself. Okay, so let's see the proof. So he is going to define so you write phi of x is equal to so okay, so maybe the way to think about it is okay, I find it most easy to think of this as a matrix. Okay, so how do you think about this? GLV, just think of it as a n cross n matrix. Okay, okay, then this is our phi. This is our given rational representation. I am trying to prove that it's a sum of one-dimensional representation. Okay, so phi of x is in G. What is phi of x? You can think of it as a n cross n matrix. Okay. Now, I look at the first 1, 1 entry, right? So the 1, 1 entry is a function. Correct? Now, I can write it as a sum of characters. Right? So, this, okay, so I'll explain this by means of an example. That's, so A chi R, let me see, n cross n matrices. Or, if you want to write formally without reference to matrices, you will say are elements of end of V. This is what you want to say. That's instead of saying n cross n matrix, this is how you have to say it if you want to say it in a coordinate free way. But let us just, okay, here is, let me explain this. So let's think of phi as a function, right? Phi as a function from G to n cross n matrices. So correct? So there is a bunch of functions, right? Okay. Now each phi I j is a linear combination of characters, right? You take the first function, write it as a linear combination of characters. Take the second one, write it as a linear combination of characters. There are n square of them. For each one of them, you write it as a linear combination of characters. Okay. Totally, the number of characters that appear in all these expressions is finite, right? So I take that set, call it some big set of characters, n characters. Each one of them now, by thinking of appropriate zero coefficients, I can think of each one of them as a linear combination of a fixed finite set of characters, right? And so if those characters are let's say chi1, chi n, then I know that this is equal to a111 chi1 plus a11n chi n, where the notation is clear now, where I am expressing phi 11 as a11 chi1 plus so on, and then the general term will be a11 ann 1 chi1 plus ann n chi n, right? Okay. Now that you can write as, now what are these a's? This is equal to, right? Now you can write a111, a121, ann1 into chi1 plus ann, a11 n, a12n, ann n into chi n, right? That is this, right? I mean, of course, x is general, so you can omit it. Right? Is this clear? We just, and by the way, is it clear also that these are unique? Why?
It's a basis. For each element, it's a basis. I mean, phi 11 and phi ij.
Because the chi i's are linearly independent. So that is the only expression possible. That's the only expression possible. This is a unique expression by Dedekind. There is a unique expression possible. So these are indeed are uniquely, actually they are uniquely determined elements. That's the only way you can write it. Okay. Now, so here are some comments he makes. Now these should be clear from okay, the properties of these a chi's. Right? A chi equal to 0 for almost all chi. That is because in this expression, there are only finitely many that are involved. Okay. Okay. Okay, then the next claim is A chi A psi is equal to delta chi psi A psi. This requires some proof. The first one is almost immediate. So this we have done. This is a claim. So this is a claim. And furthermore, that I have okay. So now you have a bunch of matrices which are projections, which are orthogonal projections in the sense, in particular, A chi is A chi. So remember, something is called a projection if p square equal to p square equal to p. So this is an endomorphism or an n cross n matrix, if you wish, whose square is itself. So it's a projection. Okay, they are orthogonal, and their sum is 1, right? So you can write, so once the claims are proved, you will get that. So V is equal to direct sum of, this is direct sum of of image of A chi and on okay, I am not saying this need checking. Okay, so once we check that, so this is a claim, if you wish. This is a claim. This is a claim. Okay. Then we are done, right? So why? Because now I choose now a basis for im A chi. So I wanted to choose a basis of, so what is, what is it, how is it a direct sum of one-dimensional representations? Well, you write each im chi A chi in any which way you want as a one-dimensional direct sum of one-dimensional spaces. So finally, for now we are assuming all these claims, right? This, and this. This follows from, given these two, the first one follows, right? Because, okay, how does the first one follow? Take an element of V, I multiply this by V, I mean apply this to V. V is equal to sum of A chi V. A chi V is of course in the image of A chi. So it proves that V is contained in this sum, right? Now, why is this a direct sum? Suppose something belongs to A chi and it belongs to A psi. Well, multiply by A chi on both sides. This side is, you will get back A chi V, but then on the other side you will get 0. Okay? Or more generally, if you take a few of them and then write it as a, the fact that if in general, if you have P, Q, R, S, various linear transformations, each of which is a projection, that is P square equal to P, Q square equal to Q, so on. Furthermore, if P, Q is equal to 0, if all of the products are 0, right, and their sum is 1, then indeed it follows easily that V is equal to the direct sums of the images. Okay? So this follows, and then finally, let's observe this also. This is also a claim. So the claims are 1, 2, these 3 claims we have to prove. This is also a claim, but that is okay. That's easily, that we did. But once this is done, we are through, because finally, I had to prove what? I had to prove 3, right? I had to prove that V is a direct sum of one-dimensional representations. Where are the one-dimensional representations? The answer is, you take that Im A chi and write it as a dimension, any which way you want as a sum of one-dimensional representations, one-dimensional vector spaces. Each line, meaning each one-dimensional subspace of Im A chi, is a stable for the action of G, right? And then you're done. Okay. So V is equal to write V as a sum of one-dimensional representations. Choose write A chi, image of A chi, as a sum of one-dimensional subspaces, any which way. Right, let me say each, right, and then put them all together. Meaning you take A chi 1, A chi 2, A chi 3, etc. Look at their images, they are subspaces. Right, this subspace is a one-dimensional sum of lines. The next one is a sum of lines, etc. And take the whole set. That will do the job. Okay. Now we have to prove. So finally, it remains only to prove for the theorem itself, because we have done 1 implies 2 and 3 implies 1 already. 2 implies 3 is what we are just doing, and we've reduced it to those 3 claims. So let's give them some names. Right? Okay, we'd only have to do that. Okay, let's see, and what he says. He says just it's okay. So the short proof, this is what all the book says, is that use. So idea is use Dedekind on G cross G. This is what he's saying. That's all there is. Okay. Of course, we have to now expand on this and see what he means by this and write it out, and that will give us the proof. Okay, so the book only will help us so far. The rest we have to do. We have to see what it means, what he means by that. Okay, let's see. Okay, phi. Now let us take, so let's try to prove 1 A, right? Okay. Okay, it seems natural to try and do phi of xy is equal to phi of x, phi of y. Right, because phi is a homomorphism, and so let us write this out. Okay, so what does this mean? Phi of xy would mean chi in chi, psi of xy a chi on the one hand, I'm just substituting xy into this equation. I mean replacing x by xy. I'm writing the left hand side. Okay, this I know, so I will know this. So now what is this? Phi x is this. Phi I would be same. Phi y would be with y here. Okay, so what I have is, but of course there are two summations, so I will use two symbols. Okay, so chi eta chi x eta y a chi a eta. Okay, maybe to make it look closer to that, let me use right. I've just substituted for this and this and multiplied out those two things. Okay. Now that sort of looks, I have a chi a psi here, right? Okay. Now I can use a dummy substitution on the other side, and I can write. So what I mean is, I'm going to write this as I'm going to, so chi of x that's just a trick of, I want to make it look like that. So instead of a double, so I have, instead of this a chi here, I have written it as a chi summation over psi. So what I have done is, instead of a chi, of course I can write this as summation over psi delta chi psi a psi, right? I have written like that. Okay. Now chi x y is of course, so then how did I get this? Chi of x y, okay. So there is a chi of x y here, put a chi of x y here, right. This chi of x y I can write as chi x chi y, because it's a character. Then there is a delta chi psi here. So I can change this to a chi and nothing will change. Because it's 0 if chi is not equal to psi. Since, okay. So listen, so
Yeah, that's fine. But only when you sum over chi and psi.
the chi is already there.
Okay.
This sum is already there. I have just written this as a sum, right, and then used a trick to here chi. Okay, now that indeed looks like what we want. If only if you can say the correct words. Right? What is it that you want to say? This is a matrix equation. Never mind the matrix equation. You can think of it as some, as a bunch of several equations. See, writing a matrix is just a way of collecting together several equations. Okay. So now each one, see, these are all, you are writing a linear combinations of characters on G cross G. These are characters on G cross G. They are distinct. Okay, so here is what you where to write here. Let me write it here. So we have this equation, right? Now what is it? We have, there are two matrices, right? Remember this what to say? Well, let me say it. I'm afraid I cannot say more than this. So what I want to say, so let us look at so let us first observe that. Okay. So what do we have to show? So this is a claim. And come to think of it, this is sort of tacit in what he's saying. He's not even making this claim, but it's, when you think about it, this is a claim you have to make and you have to actually prove it. Okay, think about the proof. Okay, so that's a claim. Let's think about the proof of that. Okay, what are we saying? We are saying, is there a map? Right? Is there a map this way, that way? Yes, indeed, there are maps. Right? So G cross G so So that gives us a map from map this way, right? So this tells us there is a map this way. Correct? Okay. Now, how do I get the other way map? Well, I have a think of embedding G. Oh, let's do it even more, slightly more generally. Let's do that will be clearer. Okay. Now, how do I get the map the other way? Well, you can think of G as sitting inside G cross H, right, by G going to G comma 1. And then if you are given a character here, you can restrict that character and that will give you the first projection. Similarly, you have a second projection. And then prove that these maps are inverses of each other. Okay? Okay. So what does that tell us? So characters of G cross G are, yes, they are characters here, time character here. So this sum is actually, you can think of that as being sum over characters in G cross G, and they are distinct. So they are distinct characters in G cross G, right? So that is, if for to say that, see, I cannot choose. See, if I choose some other chi prime and psi prime, and do this, that will not be the same character as chi and psi. Chi prime and psi prime, if I do, those will be distinct. Okay? So no two of them will be the same. So it is in fact a sum over distinct characters, and then you can apply Dedekind to say that this is equal to this. Okay? Right? Okay. So since we are out of time, I have to stop here. So the best thing perhaps is, I hope you get the idea of this proof, right? So what I will try to do is write out in some detail the proof, okay, like all this. Okay, I will try to express this proof in some, expand on what that few lines say is written into a proof, and I will send it out, and we will consider, because the rest each one of us has to read and understand. Okay, so the idea is this: you have to somehow think of Dedekind on G cross G, and then think of it in that. Okay, so that will finish the proof. So, and if you have any questions, we will answer on Friday. Okay, so we consider that these claims are proved. I have not proved them here, I understand, but I will write out the proof and send it out, and you are expected to read the proof. Okay? Okay, then see you on Friday. And how about the schedule of the exam?